We're going to discuss how to simulate an additive random walk model in at-risk and then graph the results and analyze the simulation solution. So here we have a series of data that's 20 observations long, and it's a series of sales for a company. And we have here 20 periods worth of sales, and our goal is really to simulate another 6 periods of sales. So one way to do that is just create 6 more lines at the bottom here of the worksheet. Now, what we want to do first is determine whether this series of data is correlated, whether there's autocorrelation in the data. So the way we do that is use the correlation function in Excel. And because we're measuring autocorrelation, we would first capture all but one of the observations, 1 to 19. And then in the second range of the function, start with observation 2 and go through the last observation, 2 to 20. And so the correlation is very high, positive correlation, almost 0.93. To statistically validate that we have autocorrelation, we use the Durbin-Watson statistic, and that would just be the autocorrelation times the square root of the number of observations, which is 20. And our rule of thumb is that the Durbin-Watson statistic is greater than 2 in absolute value in this case. In other words, it could be a negative number, and if it's greater than 2 in absolute value, we would say autocorrelation is present. In this case, it's positive. So we need to treat this as a correlated time series. Now, what we can do, since we know the correlation is present, is potentially try to model the differences. And so we'll calculate the differences as first the second observation minus the first, and then we'll copy that down. And we get some differences that are positive and some that are negative. Our question is, are these differences now correlated year to year? So we'll measure the autocorrelation of the differences. And so again, we start with the first observation. Of course, that's period 2 for the differences. And we'll leave out 1. And then in the second range, start with the second observation and go through the last one. All right, and now what we have for autocorrelation of the differences is a much smaller number, so let's calculate the Durbin-Watson statistic. In this case, we have 19 observations for the differences, and our Durbin-Watson statistic is smaller than 2 in absolute value. So the rule of thumb is that when Durbin-Watson is less than 2 in absolute value, there is no autocorrelation. Now, where this will be helpful in our case is to model the differences. So what we're going to do is go ahead and simulate a random variable for the differences. So let's just take the mean and the standard deviation of the differences. Calculate the mean using the average function in Excel. Mean 16.03, And the sample standard deviation, stdev.s, is 34.29. So in each of the future periods, we're going to simulate a random variable for the difference. And for now, we're going to assume this is a normal random variable. So let's go to @risk. And we want to enter a distribution and define. And so normal distribution appears, so let's select that. And we're in the cell for the first difference. And so we want to use a cell reference, so let's reference, using this little red arrow, the mean of our differences. And then for the standard deviation, let's reference the standard deviation. You notice here when we do these references, it takes off the absolute references and the dollar signs. So we'll have to enter those before we copy this assumption. So if you double click in the cell, we see we have an at-risk normal distribution assumption, and we're referencing the mean and standard deviation. Let's put a dollar sign or absolute reference in front of the mean and standard deviation row so that we can copy this down. Because these are autocorrelated, or because there's no autocorrelation in the differences, we can just treat these as independent random variables. All right, so these are the actual sales. And let's in column D calculate the forecast. I'm going to calculate in a separate column. It'll make it useful for creating a graph. So we'll jump off in our forecast column from the last actual observation. So the graph will overlap at that point. But then as we move on down, our new forecast will be the previous observation plus the current difference. The previous observation plus the current difference, and so on. Now, what we would typically, in all likelihood, want to do is say if this is a forecast for sales, we might be using this in some kind of budget or profit model. We might want any of these potentially defined as outputs. We'll just define the last one as an output in this case. So we'll have this be the period 26 forecast. And then let's go ahead and set up a graph in Excel. So let's highlight the first two columns for the moment. Highlight all 26 periods. There are some blank rows here, but that just means that in the line chart for the actuals, it'll have blank rows at the end, and then we'll graph the forecast for those observations. And so if we go to Insert, one good chart could be the line chart. And let's try this one, which is a line with markers. Okay. And so here is our actual series of values. In this case, this series here showed up also as a series, but let's change that. And instead of this being a series, let's remove it. And that's all we really want, is just the values there. And then let's add a series. So if we right-click here and do Select Data, we can add the forecast column. Now there's a number of blank cells at the beginning of the series, but it'll capture the remaining cells. Actually, let's do that a little differently. Let's right-click, select data, and do add. And so our series is going to be forecast. And it'll look like that. Okay. And so we see out here at the end where, in terms of our forecast, where this is headed. And so that's how we can graph that. Now, if we want to simulate the results for the last period, we can do that. And we see the range of values for the period 26 forecast. We see here a 90% certainty interval with 90% certainty. Our period 26 sales are between 393 and 671. We can move these sliders outward and capture other percentages if we choose. We see the mean is 538.9. And we have a lot of different percentiles here. The 10th percentile means, for instance, that 10% of the period 26 sales values are below 433.55. So this is a way we can simulate an additive random walk using @RISK.